Good afternoon again, everyone. It's Mr. Lodge, and we are dealing with part 2 of the physical science preparation for the final exams. I trust that you have already watched part 1, which dealt with the skills and the strategy involved with answering your question papers. This particular video focuses on the content and the highlights of what you should expect in paper 1 and paper 2. It also will draw your attention to common pitfalls which you need to avoid in order to achieve the best marks possible. So, without further ado, let's continue into the paper, into the presentation. Now, just remember that there's a formula. P plus E equals MOS. Potential plus effort equals measure of success. Everyone's got some potential. So what it boils down to is your effort determines your measure of success. So by putting in all the effort ahead of the time, it's going to determine your level of achievement in these exams. Let's get to some general things which I have referred to in the previous slideshow, in the previous video. Definitions need to be learned precisely and word for word. The vector nature of quantities is very important. When we're dealing with something like velocity or force or momentum or acceleration, you need to interpret its vector nature right from the beginning when you read the question as well as when you answer the question. We give signs to the vectors according to our initial description. You can decide which direction is positive, east or west, north or south, up or down. And then your final answer needs to be interpreted in terms of that direction. You're often asked to calculate the change. Could be a change in velocity, change in mass, change in kinetic energy. And there's a formula for change. This general formula for change is final minus initial. It seems back to front, but it's the final minus the initial. And we give the symbol for that a delta. It's a triangle that precedes the quantity we are talking about. Just a reminder to show all your working clearly, work from the equation step by step to a logical answer which should be expressed in a sentence at the end. Just a short sentence, especially if there's a vector nature to your answer. Remember, as I said in the previous video, to avoid proper fractions, quote your answer to 2 decimal places and include the correct unit. For longer explanations, we're going to shorten the time we spend writing by using bullet points. I'll demonstrate the bullet points to you shortly. And then lastly, often an equation can replace 1,000 words. By just linking your explanation to an equation, you can have a very short way to deal with a tricky question. Let's start off with Newton's laws. Now, Newton's laws are all about forces. And forces are vectors. And there's usually more than one force acting at a time, and there are angles between the forces. So you want to make sure that the angles that you are dealing with are in degrees and not in radians. And you protect yourself by doing that. Set your calculator to work in degrees before the start of the exam. Especially if you're an applied maths candidate, they do ask you to work in radians. So make sure you are set to degrees. Forces are not always along the x or the y axis as we would like them to be. Forces can act at angles, and we've got a way to deal with those forces by resolving them into components. So a force can have a vertical and horizontal component or a parallel and perpendicular component. and we'll use our trigonometry knowledge to resolve the force into those components. So you need to be familiar with dealing with right-angled triangles. When it comes to drawing the free body diagrams, remember not to make them too small so that nobody can see what's going on. You need to have 5 or 6 lines in which to draw the lines and then very carefully draw the tip at the end of the line, indicating the direction of the force. So the triangles that you will be drawing are a combination of arrows. Make sure that there are arrows at the end of each line. And then each arrow needs a label. For instance, the gravitational force, which always acts vertically down, Fg, needs to be labeled as such, not F earth or F gravitational or some other description you might come up with. It has to be according to the standard assessment guideline or the examination guideline. Now, the free body diagrams need to be drawn in such a way that the forces are acting away from the object that they are applied to. So we start off with a small dot, and then the forces, taking them one by one, are drawn with the tail of the arrow on the dot and the tip pointing away from it, as I will show now. And then include as many angles as you can on your free body diagram. So let's consider an object which is being pulled up a slope by a force of 100 newtons at an angle of 40 degrees. And let's say for the initial situation that this slope has no friction. And there are a number of angles here. There's the angle for the force, which is 40 degrees. There's the angle for the slope, which is 35 degrees. So we start identifying the forces that are acting. The first force would be the gravitational force. The second force would be the applied force. And the third force in green there would be the normal force, which the surface exerts on the block at 90 degrees to the surface itself. Now we move those forces, keeping them the appropriate length across to the free body diagram. So there's the free body diagram showing those 3 forces, but at the moment there are no angles shown on the diagram. The one which could be shown at the moment is the angle 130 degrees between the blue arrow and the red arrow. That would be 130 degrees. We label them either by writing them out in full or by their abbreviations, Fg, Fa for the applied force, and Fn for the normal force. Now we're going to look at resolving these forces into their components. If we look at the gravitational force, it's got a perpendicular component which acts straight into the slope. And the other component is a component which acts parallel to the slope. That's the force which pulls the block down the slope rather than into the slope. So in our minds, we have separated the gravitational force into 2 components. And there are equations for those forces given up in the top right-hand side, the perpendicular component as well as the parallel component, and they are come from the right angle there. So we've got sine theta and cos theta for those components. In the same way, we can get the components of the applied force, that 100 newtons acting up the slope in the x direction, or just directly up the slope, using Fax equals Fa times by cos theta, and then the y component would be Fa times by sine of theta. Now we're going to look at how to calculate the size of the normal force. The normal force, in order to calculate it, we need to look at all of the components acting normal to the slope. And we'll see here that there are in fact 3 forces. There's the normal force, which we're trying to calculate, and then there's the perpendicular force, the perpendicular component of the gravitational force acting downwards, and then there's the vertical component of the applied force shown in red. And the normal force will be the difference of the two. The resultant force is 0 in this case, in the direction perpendicular to the slope. So by using this formula over here, we could now calculate the normal force. So this just highlights a common error that students tend to make, that the normal force is always equal to the gravitational force. This is not the case if there are other forces acting perpendicular to the slope. Some other mistakes which are common, which come from examiners' reports: try not to use the equation delta P equals 0. Learners often confuse the signs there, mixing up the directions with gained and lost momentum. Rather use the equation the total momentum initially is equal to the total momentum finally. And that corresponds to the definition of the conservation of momentum, which states that in an isolated system, the total momentum is conserved. Another common error is when dealing with the work energy theorem. One needs to identify and calculate the net force and multiply that by the distance for which it is applied, and that is equal to the change in kinetic energy. And note this, the change in kinetic energy has to be calculated from the final kinetic energy minus the initial kinetic energy. You cannot just subtract the two velocities and substitute them into the equation for kinetic energy. So it's wrong to do that. Let's have a look at fields for a moment. There's a big difference between a field and a force. A field is a region of space in which an object experiences a force. So they are not the same. Now, in the gravitational field, the biggest mass around us is the Earth. So we're in the gravitational field of the Earth, and that sets up a gravitational field, and all other masses, let's call them little m, they experience a gravitational force in the Earth's gravitational field. Likewise with charges. If you have a very big charge, such as around a Van de Graaff generator, the electric field is set up around the big charge, let's call it capital Q. All other smaller charges, such as little pith balls, they will, let's call them little q, they will experience a force because they are in the presence of that field. Something to take note of is that magnetic fields and electric fields are not the same thing. Electric fields run from positive to negative. They act on charges, and the definition and the direction of the lines is from positive to negative. Magnetic fields, however, they exert forces on magnetic poles, and their direction is shown on the direction that a north pole would experience. The magnetic field lines exit north poles and enter south poles. Let's have a look at some common errors that are encountered in dealing with circuits. Ohm's law. In Ohm's law, it's important that you mention the current first. The current in a conductor is directly proportional to the potential difference across a conductor, rather than the other way around. So if you're looking just at Ohm's law, I, the current, depends on the voltage. But I must clarify, in certain experiments, it's possible to arrange that the current is controlled by using a variable resistor. So we can control the current, and then the current becomes the independent variable, and we would draw that on the x-axis. Another common mistake in circuits is to calculate the equivalent resistance of two resistors in parallel. We all know the formula, 1 over R parallel equals 1 over R1 plus 1 over R2. But this is where the mistake comes in. It's in the mathematics. The answer is correct, but we have to correct this. We'd rather say that Rp, where we put the parallel resistance on the top, is equal to the inverse of 1 over R1 plus 1 over R2. And that does, in fact, give you 7,5 ohms. So you would lose your marks because the mathematical step is incorrect in the first way we have dealt with it. Let's talk about chemistry for a moment. We need to know the difference when we're talking about particles between ions, which are charged particles, atoms, which are individual particles representing the smallest part of a periodic table, an element on the periodic table, and we need to know about molecules, which are more than one atom joined together, bonded somehow. We need to be able to distinguish between intermolecular forces, which is the forces between molecules on the whole, but also between some atoms and some ions, and chemical bonds. We need to be able to distinguish between those. We need to identify the intermolecular forces correctly, knowing that the London forces are the weakest, then the dipole-dipole forces are stronger, and then the strongest are the hydrogen-type intermolecular forces. We need to explain their effect on the physical properties of the substance, and also be aware that there can be more than one intermolecular force acting at the same time. They have a cumulative effect on one another. We need to be able to explain the origin of the intermolecular forces. If we turn more generally now to temperature. Temperature is directly proportional to the kinetic energy of the particles. And we need to be able to explain the effects of the temperature, changes of temperature on the particles, how it will affect reactions especially. We also need to draw attention to the fact that it's the concentration of a substance that affects the initial rate of reaction, not the amount, as will be shown in the next slide. A common mistake is not to separate the fact that electroplating is a special case of electrolysis. So the word electroplating and even electrowinning for purifying particles, purifying elements, needs to be used when appropriate. Then also, when it comes to writing down symbols for particles, we need to be very particular whether this particle has got a charge on it or not. If there's a charge on it, we need to indicate that charge on the top right-hand side of the particle. For instance, silver plus ions need to be indicated as such with a positive sign over there, rather than just silver atoms. Dealing with rates and energy, we need to remember that the rate of reaction all depends on the unit volume. So it's not just the amount, but it's the amount per unit volume. And the rate deals with the number of collisions or product produced per unit time. Leaving out per unit volume or per unit time will cost you your marks. Now, we need to be able to link the effects of temperature, concentration, the catalysts to the final outcome, and we can't just do that in one step. I'd like to show over here how one does that. Let's say we've got a decrease in concentration. How we would guide our way, rather than writing a long essay, to our final conclusion, what the effect would be. So we could, for example, say if we have a decrease in concentration, that means that there are less particles per unit volume. Next bullet. This means there are less total collisions of reactant per unit time. So therefore, there is a decrease in the number of effective collisions per unit time. Therefore, there's a lesser reaction rate. So by using bullets and one bullet per line, we can reduce a long explanation and demonstrate our thinking clearly. Let's have a look at the graphs I spoke about earlier. The most important thing on any graph is to have a look at what is on the y-axis. What is in fact being measured? And in this case, we've got the amount of hydrogen gas that is produced in centimeters cubed against time in seconds. Now, if we look at things on this graph, if we want to look at the rate would be given by the gradient. How much hydrogen is produced per second. So we would get our average rate given by the gradient up to a certain time. Then what influences the end amount of hydrogen? The final amount of hydrogen, as shown up over here, is dictated by the amount of limiting reagent. The reagent you're going to run out of first will determine how much hydrogen will be produced. And then lastly, the time. How long will it take to reach your final product? That's affected by two things. It is your average rate as well as your limiting reagent. We could apply this the same thinking to, let's say we've got a catalyst which is stimulating a reaction. Sorry, the way it is described here, it's not a catalyst, it is the limiting reactant. It could come in different forms. In purple, we see it in large chunks. In orange, we see it in small chunks. In green, we see it in a powder form. And in blue, we double the amount of the limiting reactant. But the same thinking applies as the previous slide. Let's talk about Le Chatelier's principle for a moment. Le Chatelier's principle guides us as we look at systems in equilibrium, which need to be closed and involve reversible reactions. The first thing we need to do is have a look at what stress has been applied to the system which is already in equilibrium. It will either be a change in temperature, pressure, or volume. Now we need to use Le Chatelier's principle to think which reaction would be favored, the forward or reverse, in order to minimize the effect of the stress. And then we would reason, how does favoring the forward or reverse reaction relieve the stress according to Le Chatelier's principle? So for instance, if we increase the pressure, one of the reactions would be favored in such a way as to decrease the pressure. And we would use bullet format to explain that. When we use the word favored, it does not mean that the reaction gets faster as such. It just means that it increases more or decreases less compared to the other reaction. So favored is a relative term. Just a note to remember how to use Rice tables, where your ratios, your initial concentrations, your change, and your equilibrium concentrations are all tabulated. It's standard bookwork. It will be asked. It's a guaranteed long question, so practice some Rice tables. Let's turn our attention to acids and bases. In acids and bases, there is a distinct difference. Acids react with water. There's an ionization process taking place where the acid molecule and the water molecule interact with one another to form two ions, as is clearly seen over here. The hydronium ion, H3O+, and the acid anion, in this case, the chlorine anion. If you look at a base, for instance, sodium hydroxide, the sodium ions exist already. They're in the substance. The hydroxide ions are in the substance. When one puts that substance in the presence of water, all we're doing is dissociating them. So the term there is dissociation, which means that they get further apart, and it's a type of separation. The ions were already there. So dissociation is a physical change, whereas ionization is a chemical change. There's one exception to this, and that is when we have ammonia reacting with water. And when ammonia reacts with water, as it says over here, we have molecules, the ammonia molecule and the water molecule, forming the ammonium ion and the hydroxide ion. That's just something that you do need to remember off by heart. Remember, when dealing with these chemical equations, as is the case always, look for the mole ratios. How many moles of acid are forming how many moles of the hydronium ions? Watch for polyprotic acids. Polyprotic acids give more than one hydrogen across to the water. And also, in the case of a base, it's possible that you could have more than one hydroxide in the substance per formula unit. Just a common mistake is that when we are using just the concentration of a substance and we want to explain that, you're allowed to use square brackets around that substance or species. But when you substitute that value into an equation, you must use round brackets, not the square brackets. So let's turn our attention now to electrochemistry, which constitutes 20% of your exam. So you want to be confident about this section. Now, understanding this section hinges on your table of electric potentials. And right in the middle of that table, you'll find the hydrogen electrode, the standard hydrogen electrode. It has got 4 conditions around its voltage. The first one being that there's a platinum electrode connecting the acid, which has got a concentration of 1 mole per decimeter cubed, and the gas, the hydrogen gas around it, at a pressure of 1 atmosphere. The other condition around it is that the temperature needs to be 25 degrees Celsius. Now, as you look at the other electrode potentials on that table, they do not necessarily have as many standard conditions. For instance, the tin electrode does not need a platinum electrode because the tin itself is an electrode. There's no gas around the tin electrode, so that standard condition falls away. So when you are asked for the standard conditions, make sure that they are specific to the electrode that you are talking about in this question. The electrochemistry, there are certain things that you need to know backwards. You need to know which electrode is positive, which electrode is negative. In a galvanic cell, the positive electrode is the cathode and the negative electrode is the anode, for instance. You need to know at which electrode is oxidation taking place? At which electrode is reduction taking place? You need to know that galvanic cells have got an E0 greater than naught, and they are spontaneous, whereas electrolytic cells, you need to put the energy in there, so they're non-spontaneous and they've got an E0 of less than 0. You need to be able to combine the two half reactions, one happening at the one electrode, the other at the other electrode, to form a balanced ionic reaction equation. And that is not new work, it's something you would have practiced many times. Let's have a look at this section here on chemical bonding. And this is one of my favorite sections because it describes in so much detail the behavior of substances. For instance, the water that we drink, which is H2O. Now, there's two things happening in H2O. There's the bonds between the hydrogen and the oxygen, and we call them the intramolecular bonds. That's between the hydrogen and the oxygen. The other thing which is happening there is the bonds between the molecules, or the forces between the molecules, and that is how each H2O interacts with each other H2O. So we need to be able to differentiate between the intramolecular bonds between the hydrogen and the oxygen and the intermolecular forces between the different molecules. We need to be able to classify the bond type in full. So just to say it's covalent or ionic is not good enough. We need to say this is a non-polar or a pure covalent bond or a polar covalent bond. When comparing and explaining compounds and their physical properties, we need to be able to identify and name the relevant intermolecular forces. We need to compare and see which one has the stronger intermolecular forces. Then we need to look at which are the factors making that intermolecular force stronger or weaker. And then when they talk especially about overcoming those intermolecular forces, we need to refer to the amount of energy required to overcome them. Now, this relates to melting points and boiling points. So, when we're dealing with the intermolecular forces, we overcome the intermolecular forces. When we're dealing with chemical bonds, we break the bonds. So, there's a clear distinction between bonds which are broken. So the intramolecular bonds get broken and the intermolecular forces are overcome. Let's have a look at the last big section, which is organic chemistry. Now, organic chemistry is one of those sections which you can really rub your hands and look forward to. Because if you just study this off by heart, you are guaranteed a good portion of marks here. So I want to start off by saying study, study, study. The common mistakes in organic chemistry come from not reading the question. If the examiner asks for name the molecule, he means name the molecule. And that can be 3 to 4 marks because there are some quite complicated molecules. If you, on the other hand, instead of giving the name, give the molecular formula, which is the total amount of atoms, of the different atoms in the molecule, you're going to lose your marks. The empirical formula is the smallest whole number ratio of the atoms involved in the molecule. Careful for that word empirical. It's different to molecular. Then the condensed structural formula shows the number of carbons along the chain and what is attached to each carbon. Compared to the structural formula is where you draw a line showing every single bond between every single atom in the whole formula. So the common mistakes here are not reading the question, not distinguishing between condensed and structural, between molecular formula and empirical formula, even between name and formula. You will lose marks for that. In organic chemistry, they often ask you, what type of reaction is this? Now, they will ask, what type of is the general type of reaction, or what is the specific type of reaction? So, for instance, you might have an elimination reaction which removes 2 atoms from the molecule or more atoms from the molecule, and it would be called elimination. But in the specific case, they might ask you to name that. It might be dehydrohalogenation or dehalogenation. They might ask you for the specific type of reaction in the question. Remember that. When it comes to the naming of molecules, remember the euphonic rules, which have recently come into play. So I would focus some time on learning these, and it is given to you in your notes, that we refer to butane 1-ol, not butane 1-ol. It just sounds better. And when it comes to the diols, then we say butane 1,2 diol, not butane 1,2 diol. That just needs to be learned. The diols, you keep the E. When we have the dienes, we shorten it. We take off the an, we just say buta 1,3 diene. So remember the E's are included for the diols, and the Ne is excluded for the dienes. Let's close off the session by looking at some scientific skills which deal with data handling, or in mathematics, you'd refer to it as statistics. The terms we're going to use are precision, firstly. Precision has got to do with the range of answers that your experiments produce. A precise experiment produces a very narrow range of answers that you are calculating. Accuracy refers to how your answers compare to a known value. For instance, G equals 9,8 meters per second squared. If your experiment gives you an answer very close to 9,8 meters per second squared, it is said to be accurate. Validity refers to the fact that your experiment can be repeated under the same conditions anywhere on Earth. It's not space or person specific. Anybody can do it. It's a valid experiment. To be a fair test, it means that only one variable is changed at a time, so that the effect of the variable is very clear on the outcome. So there's only one variable which can have affected the outcome of the experiment. Quantitative analysis is all about the numbers that come from the experiment, and we're dealing with answers in terms of numbers. Whereas as qualitative would be things like chemical tests, which give you a yes or no answer. For instance, when you add bromine water to a double bond in organic chemistry, you would have a qualitative answer. Yes, it discolors, or no, it does not discolor. We should know the steps of the scientific method, and you might well be asked to describe where you are, or describe a method, or even write out a method, design a method to test something. You might be asked to suggest which experiment, which apparatus is required for a certain experiment. For instance, to measure the rate of reaction, you might need a gas cylinder which is graduated. You might need stopwatches, you might need scales, etc. You're going to have to apply that to a given situation. And then lastly, sources of error. No experiment gives us the exact answers we expect. And the examiner might ask you, what are the possible sources of error? A common failing that candidates write is, it's a human error. Now, unfortunately, there is no error in being human. The error would lie in a measurement or in the design of the experiment, somewhere like that. Just to let you know, human error is not one of your options. And that is our session on Physical Science Paper 1 and Paper 2. Do spend some time going over both of these videos and make notes, practice it on your own, study hard, and all the best for your final exams.